Hello everyone, I'm very happy to be with you on this very first DConf Online 2020. My name is Ali Çehreli. I've been with D since 2009. Coming from C++, it was a love at first sight for me. As soon as I read Andrei Alexandrescu's The Case for D article, I immediately translated it to Turkish, created a Turkish D site, and then I ended up writing programming in D, which I'm known for in the D community. I consider that book to be a happy accident, and which is recently available on Educative.io as an interactive course in 2 parts. I currently work at Mercedes-Benz Research and Development, North America, and we use D for ROS-back file manipulation for autonomous driving. And all of these links are, of course, live on my slides. This one is a link to my 2019 presentation on the topic. This is a project between Daimler and Bosch, which I consider to be a happy place. After this introduction, I will talk a little bit about engineering with D, what I think about engineering with D, and I'll give a mini experience report since my DConf 2019 presentation, and then I'll get into not very well structured, just various productive features of D that I extracted from my code. I just literally browsed my code and found some useful bits and pieces here and there and put them together for that section. 2 main ones, I think, 2 extremely useful ones are parallelism and concurrency, and there is more. And the numbers at the corner of the slides are not number of slides, they are just clicks that I go through the slides. I think engineering with D involves few bugs, or fewer bugs compared to the other languages that I'm experienced with. I find D to be a very productive tool, and I still have, after decades of software engineering, I still have a lot of fun writing in D. And subjectively, I think D made a better engineer in me. Looking at my pre-D self, I'm a less perfectionist person, which may be good or bad, but sometimes it puts into a locked state where you can't move forward, so perfectionism is a problem in that case. With D, I'm less perfectionist, more pragmatic, and I'm someone who acknowledges organic growth. D today is a 20-year-old language, and it ends up having certain levels of warts in it. For example, no GC has @ character in front of it, but pure doesn't. And this really does not bother me. And I realize that I can afford to be not very much principled in my coding. I just directly go to the results, just code the way I want. And then as requirements change, or as I'm not happy with the certain code style, I just change my code. I realize that D has less friction in this activity, and this has been advocated by Liran Zwiebel and Leith Ishark. And again, I have 2 links for their DConf presentations. D provides plasticity. I will show you 3 features of D which helped me become a more pragmatic person. The first one is unit test. As D programmers, we enjoy this feature tremendously. One of the most useful features of D. If you have a function, let's say like halved on this slide, you can create a unit test block right under it, which tests that function's functionality. In this case, it says 42 halved equals 21. And if you're new to D's universal function call syntax, 42.halved, which will appear in other slides in this presentation, is nothing different from halved called with 42 as its first parameter. Despite being so useful, D's unit test blocks are almost comically underpowered. They don't have any unit testing features that you would expect from any modern unit testing framework. For example, there are no test suites, no fixtures, no mocks, no fakes, nothing. Just assert. And assert is not a unit test tool anyway, it is available everywhere in the language. So still, being so underpowered, unit test is so powerful that enables so much for the programmer, for the developer, is that if we lost unit test today, it would be a huge loss to D. So this is one feature of D that taught me to become a better engineer, where there are certain simple, maybe stupid little things you can add that give tremendous value. The second example is static if. In D programs, we enjoy static if almost everywhere. Every program has this. The standard library enjoys this. Depending on a template parameter in this case, if t is integral, this static if is injecting a member variable to a struct. This is a good kind of magic that you would want in your tool. This is almost cheating. However, if you agree with certain arguments where this feature has been considered, and I put it in double quotes because the title of an article is that way, you can consider it to be harder to read and understand, or if you believe it provides ample opportunities for confusion and mistakes, even if you believed in it and even if you could find examples of this to be true, if you remove static if from D today, it would be a huge loss. So my second point with this feature is this is so powerful, despite its argued corner cases. We should have this in here, and I'm glad we do. The third example I'm going to show is ranges, surprisingly, because we enjoy ranges tremendously. They provide lazy evaluations, minimal memory usage. We don't allocate arrays to process our data anymore. We just process them one by one with this feature. Component programming, pipeline programming, and we reduce loops. Most of our programs don't have loops anymore, explicit loops anymore. If you're new to D's range syntax, because I will use this style in the rest of the slides, let me explain what this one does. 5.iota is basically a range object which will generate the numbers 0 to 4 inclusive. And map is a range algorithm that applies the functionality given to it to the elements that are given to it. So in this case, the overall range object here applies function foo to every element generated. So it will be foo0, foo1, etc. Despite being so useful, you can argue that ranges are not perfect. For example, algorithms like find should not and maybe cannot return a range back. Find naturally returns one thing, the thing that I'm searching for. So even such a common algorithm like find doesn't fit well with the range concept, one may argue. Or an algorithm like partition. If partition returned a single iterator, the caller could make a range from the first part or from the second part, so it would be more useful. Even if you argued with these and removed ranges from D, it would be a huge loss. So these are just 3 examples I pulled out of D's functionalities that engineering is more than perfectionism. You need these little tools that are so powerful that you should oversee their argued deficiencies. Now I get to some statistics of my code at Mercedes-Benz Research and Development. Since last DConf 2019, the number of programs and the number of code files have doubled, but the lines are reaching to maybe 3 times. The most interesting statistics for me is the number of format string literals in my 7 programs. I have today more than 500 of those. And I've shown during 2019 presentation that this kind of usage of, for example, format should be considered to be a bug. Because if the provided arguments don't match the format string literal, that mismatch is caught only at runtime. And because these string literals are used in error messages, there's a big problem because you detect some problem in your program, you want to display an error message to the user. You can't. You fail at the state of providing this useful information. So this should never be used. For that reason, almost all of my 500 plus format string literals use this compile time checked safe version. So this one, if you're not used to D's template instantiation syntax, that bang operator there actually instantiates the format template with this string, and then format at compile time makes sure that the provided arguments for this use match the provided format specifiers. This is safe, but it's getting better. Thanks to Adam Rupi and Steven Schweighofer, two very strong parts of our D community, have written DIP 1036, and DIP stands for D Improvement Proposal. We will get formatted strings tuple literals, and we will be able to embed the names of variables right inside the format strings. I thank them for this. I ran garbage collector statistics on my program. Any D program that's compiled has some hidden command line arguments. These all begin with --drt, and there are sub-arguments like -gc opt in this case. And GC, garbage collector arguments, have further sub-options, which is profile:1, which means please profile my program. And when you run your program, already compiled program with this option, you will get some statistics on garbage collector. I ran it on two of my programs, which are program 1 and program 2 on 2 lines, and I ran them with two different data sets, 60 gigabyte and less than that. What I found interesting is one program experienced a GC pause for 54 milliseconds maximum. The other one's maximum was 4 milliseconds. And even though I used 60 gigabyte of data, of course, I never allocated that much. Garbage collector only allocated 4 gigabytes for that use case. And the total GC time that I spent was 3.7 seconds of a 3-minute 40-second program. But because the program is multi-threaded, the overall user time was actually 15 minutes. So these were some observations. I just put them here as some statistic points. In my applications, garbage collector time, pause, does not matter at all. These are all command line tools, developer tools run on developer workstations. Related to garbage collector statistics, if you compile your program with --profile equals GC, then your program will be instrumented with certain machine code in it to give you garbage collector statistics, how your program uses the garbage collector. You just compile your program, execute it, and then the program will drop a file called profilegc.log, which will show exactly what line of your program allocated how much memory. In this example, line 23 of my program allocated 704 bytes 4 times on that line. So looking at these statistics, you can go to the exact lines and improve the performance of your program. I use this feature. And most of the time, the problems occur when I have an array in an inner loop. Assume that this code is a function body. I have an outer array. I have a loop where an inner array is gaining some elements. The problem here is the inner array is allocated afresh every time the while a loop iterates. So even though I use inner as a temporary array for my processing, every time the iteration ends, that allocated memory, that array's buffer is dumped and a new one is created. So the one simplest thing that I can do is moving that inner, before getting to that, let me show you one statistic of this. So the line 8 here, where I add elements to the inner array, has allocated 260,000 times in this test, and the total memory allocation was 18 megabytes. But if I move that inner array outside of the while a loop, but being careful, set the inner length to 0 and call assume safe append, meaning there is no other array sharing this memory with you, you can safely append to your existing buffer, meaning overwrite your existing buffer. If I do this simple act, now I realize that the total memory allocated is nowhere like 18 megabytes, but 800K in this case, and instead of 260,000, it's 8,000 times. But of course, don't do this, because there is already an appender which does these behind the scenes. So instead of using plain arrays, if you use appender of int arrays, in this case, outer and inner, and if I clear outer every time I entered this function, and if I clear inner every time I iterate through the while a loop, then I would see no allocation in my code, because appender will do it in a very efficient way in the library side. Now there's something very important here to mention. Some of you may think, oh, static variables, now this function cannot be multi-thread safe. This is multi-thread safe in D, because by default, data is thread local in D. So even though these are static variables, every thread gets its own static variable. So even though there are multiple threads calling this function, every thread will be enjoying its pre-allocated buffer and writing in there efficiently. However, it must be noted, thread safe does not mean reentrant. So if you call this function, and if it calls somewhere else, but then that somewhere else calls this again, the second invocation will clear your previous state, which is probably not what you want. So use this in cases where you don't need reentrancy. After this statistics related part, now I get to mixed bag of various productive D features. The first one is, just because I mentioned format specifiers, the range format specifier. This is something I use a lot. So as I reminded, 5.iota is a range, and write formatted line will take the elements of that range and apply this range format specifier to it. If you print with this expression, you will get 0, 1, 2, 3, 4 side by side. I want to decipher this admittedly cryptic format specifier. % open parentheses opens this range format specifier. % closing parentheses, the ones that I underlined with blue, closes the range format specifier. And anything in between, like %s in this case, is applied to every element of the range. So in a sense, this format specifier executes a loop itself until the range ends. So one clever thing about this specifier is, any character after the element specifier, like %s, again in this case, like the comma space that I underlined with blue, will be printed in between every element, like an element separator. So we will get 0, comma, space, 1, comma, space, etc. And one smart thing about this feature is, because it's an element separator and because there's no element after the last one, you don't get that printed after the last one. Pretty useful. However, this feature can be a little too clever. Let's say I want to print the same elements between angle brackets now, and also I want to put them on separate lines. That's why I put a \n there. If you try to print it with this expression, you will notice that the closing angle brackets is missing, because the format specifier assumes closing bracket is an element separator there, so it will not print it for after the last element. So the solution is to use %bar. Anything to the left of bar means include it for every element, and anything to the right of bar means that's the element separator. So in this case, we see that the closing bracket, angle bracket, is printed for the last element as well, and elements are separated with \n only. They appear on new lines only. Another feature of this format specifier, which I don't use myself much, is if your elements are strings or characters, they will be printed within double quotes or single quotes by default. Because they are strings, strings have double quotes. If you don't like this feature, if it's not what your program wants to do, you open your range format specifier with %- open parentheses. In this case, it means don't use double quotes for strings and don't use single quotes for characters. This I use a lot, because in my case I don't care for the double quotes. And one great thing about this feature is they can be nested. In this expression, I have a range of ranges. The 5.iota generates numbers from 0 to 4, and each one of those is used to generate further numbers. So this is basically creating a triangle of numbers. The ones underlined with blue are for the outer elements, and the ones underlined with orange is for the inner ones. So the inner ranges elements will be separated with comma space, and the outer ranges elements will be on every new line. So this gives me a triangular numbers according to my specification. And I must note there is actually an invisible range there with 0 elements. That's why we don't see anything with that. The first 0 value creates a range of 0 length. Another feature, nice feature, is if you're printing associative array elements, you can kind of flatten the %s's. So if you use 2 %s's in your element specifier area, the first one is considered to be for the key, and the second one is considered to be for the value. So if I have %s is %s, then it uses the key is value format, and I get b is 2, a is 1 in an unexpected order, because hash tables work this way. Still related to format string literals, we have decimal place separator, which I use a lot. Otherwise, I can't figure out how many digits are there. Is that a million? Is that a billion? So %, will put a comma by default at every 3rd decimal place. You can change the number of decimal places if you provide a star in the format. This one is at every 6 decimal places. You can change the character with a question mark. This one uses a Unicode middle dot character, or you can specify both, of course, every 2nd decimal place with a backtick this time. Now I get to two very nice features. The first one is parallelism. For me, parallel is one of the most impressive parts of the D standard library. If I have a loop over some elements, some range of elements, and assuming that this loop takes 4 seconds, just adding dot parallel to the end of the elements makes the loop go complete in 1 second on a 4-core system. This is, of course, in theory. In practice, this may not work that well. But the fact that you just add dot parallel and your loop suddenly goes faster is very impressive. Parallel is also impressive because it's not a D language feature. It's a library feature written with all the facilities of the language that you and I could write. Parallel is actually a function that returns a special typed object. The type of that object provides the op-apply special function, which makes that object iteratable in a for each loop. The language gives the body of the for each loop as a delegate to this object's iteration, and that object dispatches this body to different threads of a thread pool and waits for their completion. This is also very impressive for me. It has one important guideline to use it correctly. Make sure loop body is independent for each element. So the loop body, you should imagine that the loop body executes in parallel for multiple elements at the same time. They should be completely independent when it comes to the data that they mutate. Now I will show you a buggy code. Here I'm processing every element, but every loop body processing process puts a result in a results array up there. This is a blatant bug because this violates the one rule of parallel, because multiple parallel executions will try to mutate the same array and they will be in a race condition, and that's a clear bug. And there's a questionable act there. Every loop body is trying to report some progress to the user, saying, I'm done 10% overall, 20%, whatever. Because loop body cannot know about each other, every iteration of an element, this is a questionable act, and this cannot be done in most cases. I'll get to this. So fixing the bug is very easy, actually. Even if the loop body processing of every element wants to put a result in an array, if you size your array equal the element length first. Even though here the loop body execution for element looks like they are mutating the same array, they are not changing the structure of the array. They are actually assigning the result into their reserved spots. So in this case, the bug has disappeared, we fixed it. However, you should research false sharing. This may or may not hurt performance in your use case. Now I get to the questionable part. In order to report progress, you can keep a counter outside of the loop, called completed in this case, and then you can report progress with that completed number and then element's length. This has to be in a synchronized block. Now, they're really independent from each other because synchronized code is a mutually exclusive executed code which uses a mutex behind the scenes. Now we're good. But this use of synchronized makes this code questionable in capital letters now, because this has the danger of making your parallel execution completely serial. Especially if the processing of each element is so quick, all of your element processing will be lined up waiting for each other to grab this mutex lock. So you can do this, like I do this, only if your processing of every element is slow operation. For example, in my case, every element may be opening a file, processing it, and then writing to another file. In that case, if the processing takes several seconds or even a half second, you can afford to put a synchronized here, and I do this and I don't see any performance penalty. Parallel being so useful has two configuration options that you may care about. First one is thread count. Parallel will use threads equal the number of cores you have on your system. Total CPUs of the standard library is almost a misnomer because it should be total cores. So if you don't want to run this loop on all cores of your system, you can create a task pool yourself, but you must remember to finish it. I will give an example of it soon. And the second configuration point is work unit size. By default, every thread will grab 100 elements to process for itself. This is to reduce thread context switching costs. And this is a good thing in general. But in your application, grabbing 100 elements per thread might be too expensive. For example, if you're processing files, one thread deciding to process 100 files may not be as efficient. In which case, you may want to put work unit size as 1. Every thread grabs one file, processes it, and then grabs another file and processes it. And this code shows you how you can configure your parallel loop. TP is a task pool there. I just create with new. This time I divide total CPUs by 2, so I'm using half of the cores. And then tp.parallel gets the elements, and the second option, the second parameter, is the number of work units. I pass 1. As I said, I don't forget to finish the task pool, and this is how you can squeeze the best performance out of your for each loop. I recommend that you experiment with these two values because it can make or break. It's a make or break kind of deal. Your performance can go to the ceiling or to the bottom. The next feature that I'm gonna talk about is standard concurrency. I use this a lot in my programs as well. And standard concurrency provides message passing concurrency, which happens to be the right kind of concurrency for many applications. Concurrency is much more complicated than parallelism. So I've come with some experience, I've found a recipe to use concurrency to my liking. Now I'm gonna share it with you. After these slides, I will give you a single slide program where you can start as a template and experiment with yourself. I like to start my worker threads that I'm going to use with concurrency with spawn linked. This expression is again a range expression. I create 4 worker threads. I spawn 4 worker threads starting from the worker thread function, and .array there is actually an eagerness in our library. I make an eager version of this. So workers at this point contains 4 worker threads already started. And worker thread can be a function like this. Sending messages is done with send. There's nothing special there. And receiving messages, waiting for messages, is done with receive. In some cases I use receive timeout, but in my cases I use receive timeout to see whether there's any message at all. Even though you can give a duration to receive timeout, in my use case it's almost always 0 milliseconds. So the reason I like starting my worker threads with spawn linked is so that I receive a link terminated message when the thread terminates. Whenever my worker thread terminates either by success or by error due to a thrown exception, I do receive a link terminated. And I like this because my main threads loop can be this simple one, waiting while the completed thread count is less than worker's length. And inside I have a receive call, which receives a link terminated message and increments the completed count. There is also owner terminated message, where the worker threads will receive when the main thread terminates. But I don't use this in my programs. Now, another very important point is that threads have their own separate function call stacks. For that reason, the main thread cannot know whether your worker thread has thrown an exception or not. This must be handled by the worker thread itself. Each worker must catch the exceptions and communicate them in a way, either log them in a log file or send them as a message to the main thread. For that reason, my worker thread functions almost always contain nothing but a single try catch block. I try to do something, and to do something is always into a worker thread implementation function. Then I catch the exceptions and do something with them. Before getting into what I do with them, I want to remind you of exception kinds that we have in dlang language. The topmost exception type we have is throwable. That's what exceptions are. They are throwables. This is advised not to catch ever. The two subtypes of throwable are exception and error. And error indicates irrecoverable problems, which is also recommended not to catch. But exception side is happily catchable, and you can do anything you want with it. Here's an example of exception. Exception means something bad happened. For example, the user input a name string which was empty. You can say enforce name not empty, and then print some useful error message. Enforce behind the scenes throws an exception, and I use this a lot. Instead of an explicit throw new exception, I use enforce. Now you may catch this and do something and continue. Error. So you can do something. In order to catch exception, your thread can use a struct named worker error like this, which can contain a thread ID in there, which I chose to be an integer number here. Then you can have the exception object nicely wrapped in this struct that you communicate back to. But this exception object better be marked as immutable, so it better be an immutable exception. The reason is immutable is implicitly shared, which means you can pass it to your main thread. With that, my worker threads catch clause, one of them can be exception like this, and then I'm sending to my owner. Owner TID represents the main thread, the owner thread. Owner TID send, and I make a fresh worker error object here with my ID. And because I caught as exception without any attributes, I just cast it to immutable before making a worker error. If you don't do this, it will be an error. But I'm okay with this cast because I'm not going to use this object anymore. It's just being sent to my main thread. So the main thread on the other side can wait for such a worker error in its receive function, waits for it, and it receives it as const in this case because it has no interest in modifying this object, of course, and reacts to this as it wants. Now, error, on the other hand, represents an illegal program state. We can throw an error with an assert statement, assert expression. For example, in some point in my program where I expect that a certain string's length must be 42, I can check for that, and then I can print that message. I can embed a message indicating the problem in an error object, and then error will be thrown out. In theory, we are advised not to catch error, and in theory, we shouldn't even try to format an error message because the program is in an illegal state. We don't know what state it's in if this assertion failed. I think in theory you should not even abort, because abort is a function call. Is my program in a state where I can attempt to make a call to abort? So you should not do anything in theory, but it's not practical. And it's not what the main thread, the D runtime, does for the main thread. A practical approach is to catch wishfully, report wishfully, and then abort. You can change the main thread's behavior with these two options that I list down there. You can tell main thread not even catch anything. Don't trap exceptions. So for that reason, if we choose practicality over theory, your worker thread may catch error, prints the error on standard error stream, which is in itself a wishful thinking, because as I learned that certain environments like the Windows environments may not have stood error, but you have some way of logging this error, so you can log it there, and immediately I abort. This abort will abort your program, so your main thread disappears too. But I think this is this is respectful enough. I'm not even attempting to send a message to main thread now because I detected an illegal state and I stop. Error management fascinates me to this day after all these years of programming. It's a difficult and very complicated topic still. Now, passing mutable data between threads needs the data to be shared. For example, going back to the very early expression in this concurrency slides, if I spawn my worker thread with some argument, maybe an array that I allocated, maybe pre-populated, I need to pass it as shared. So I can do this cast shared my array. And I note again that immutable data is implicitly shared, so you don't need to cast immutable. And on the worker thread side, because I casted the argument going in as shared, the worker thread must take shared int. But shared int is inconvenient because most of your algorithms, most of your class member functions are not written to work with shared. For that reason, in my experience, as soon as the worker thread takes shared, I cast that shared away. So in this case, I cast it to a regular int array and pass it to my worker thread implementation. And from that point on, my code is non-shared happily ever after. Of course, shared doesn't mean you can share this data. But as you see in this case, the direction of data, flow of data is one directional. The main thread sends it as an argument, the worker thread receives it, and it's safe to cast away shared and use it, because this is for this worker thread's use only. Of course, this example doesn't provide any array with any meaningful input. It's just a default initialized array. But in my case, I prepare something for the worker thread and give that to it, casting shared and then non-casting on the other end. Okay, here's my single slide example. This example includes everything that I've talked about on standard concurrency so far. And the worker threads don't do any work other than with certain probability, they either succeed or they throw an exception or they throw an error. to show you how this program will behave in one of those three cases. And if you squint a little down there, there's a dice call to stud random module, which is very nice. So dice will throw a dice, which is not a fair dice actually, it's favoring the success case in this one. Alright, my next topic is nested functions. I find myself in code where I realize that I'm duplicating certain expressions. For example, if you assume A and B are two arrays here, I sometimes go through the same indexed element and then some member maybe reach into the color of that member, and if the color that I reach through the A element is red and B is green, I do something. And in some cases even I use the same expression in some error strings. This is called duplication, which I remove with nested functions. Instead of repeating that expression, you can have a function named color, which takes an array as a parameter and basically returns the same expression. And now my code is much more readable, which means in this case, if color accessed through the A array is red and color accessed through the B array is green, etc. And note that for each counter I there that is being used by color is not passed in as a parameter, because in this case color happens to be a delegate and uses the variables from its context. I use this feature and find it very convenient. Here's another example of it that came up on the D forums while I was preparing these slides. This one is a red, green, blue struct, which is common in web programming too. And the constructor receives an unsigned int value. And because bit shifting and masking is repeated for these three elements anyway, I write a pop low byte nested function, which mutates the argument of the parameter in this case, and then provides the low bytes distributes the low bytes in every case to these three members. Of course, in reality, after these assignments, there should be a check for whether values higher byte had any bits set in it or not. Enforce evaluates the format string lazily, because it would be wasteful if it evaluated every time. Enforce will check the condition and then evaluate this expression, which is expensive in this case. It calls a format and then the string literal is evaluated. That's good. However, I find myself in cases where almost the same error message is repeated like this. One might think of creating a local variable to put that string into it and then run the enforcement with that message. Even though this removes the code duplication, which is good, the message is now evaluated eagerly, and that's what I wanted to avoid. The solution is again a nested function. I can have a message nested function which returns this expression, and because enforce calls that function lazily, the function is called only when needed, and I achieved both of my goals. No duplication and no eager evaluation. In some cases, you may find yourself some objects have unmentionable types. These occur very frequently in D standard library features. For example, file.byline is a range object. Byline returns a struct object, but the name of that struct object shouldn't be my concern, and usually it is not my concern. It can change over time. And this is just a decidedly simple one. When you pipeline and make your range expression more complicated, it gets a bit really hairy. But let's say I want to create this range object and also have a member of the same type. What's the type of that variable to say? I can't mention it, I can't do this. So I've come up with a solution for this. If you return your range expression from a function, like this make range in this case, and for convenience I recommend make all the parameters have an initial value, And luckily, every type in D has an initial value. So in this case, string gets null. However, because calling it with null might be an error in my case, I can always put a contract check there, a precondition check. And even though I put a null there, I'm guaranteeing that this will never be called with null. So file name not empty there is the same as file name null. And then I return this complex expression. But this function, luckily, allows me to use type of make range function call so that I grab that unmentionable type this way, which I may alias, use an alias of course. And in the constructor, again, I don't repeat the same expression. I call make range, passing the actual file name to it. Somewhat related, but nothing related to D in here. Sometimes I realize that I assign a value to a variable, some value, but depending on condition, I do some other stuff. And then I need to change the value of this variable to some other value. Just because depending on that condition, I will set a different value to this A after doing something note, I cannot define A to be constant or immutable. That's why I leave it mutable. The solution is to use a lambda. So in this case, I can make my A const, where all this logic sits in a lambda expression. So it says if condition do something else, and it returns some other value or some value when the condition is false. I used this also in some places. Stud_typeconst flag is a named Boolean feature. So when you want to pass in some behavior configuration to your functions, you can say please do compress or please do not skip, as in this case. So yes compress may mean to a function do compress, no skip means don't skip, whatever that thing is for this function. The good thing about flag over plain Boolean types is if I mix and match these, it's a compilation error because these are typed as flag bang compress and flag bang skip. However, there is an inconvenience in using these flags. If I already have a Boolean variable, I can't make a yes compress or no compress directly out of it. I need to use these ternary expressions. There are other options for this, but I don't find anything else pleasant either. So there's this inconvenience, unpleasantness to it. Flag in itself is not that bad, and this use in itself is not that bad, but this reminds me of the solution. Reminds me of these alias template parameters. So this is the solution I came to this problem, mini problem. I wrote a toFlag function template that takes a variable by alias, which allows me to take the name of that variable with the dot string of property. With that name, I basically create the ternary operator myself in here, return if variable true, yes variable, or no variable, which is mixed in here, and then I execute that and return a flag compress or flag skip typed value. So my code is now nice. Foo to flag compress to flag skip. Another practical thing I discovered is using your module as a singleton object. In some cases, I have a top-level function in my module. The user of the module makes a call to this, but this top-level makes maybe, in some cases, dozens of other function calls in a function call graph all the way down. And sometimes I need to introduce a new variable to this top-level function, like the verbosity flag. Now I need to go to all those dozens of functions and set a verbosity flag in case they need it, or in most cases they need, like in this case. So instead of this, I discovered, why am I doing this? Since my module can be seen as a single object, let me have a module level verbosity variable, so the top level function can just set it to true or false in this case, And I don't need to touch any of my dozens of function interfaces, even though some of them may take advantage of this verbose value. So this is something I did, you know, pragmatic, practical, whatever you call it. But of course there's a bug in this case. Remembering that data is thread local by default, even though module is a singleton object, module variables are thread local by default. So using concurrency or parallel, I realized that only one thread was using verbosely printing logs on screen, and the solution is to mark that variable as shared. And warning, of course. So having a single object per thread may not work in your case. If top level is called multiple times by your users, they will be overriding this verbose variable, and which may not be what you want. But in my case, top level is really top level. I call this function from main, and then nobody calls it twice during the one execution of my command line program. So parsing files at compile time is actually a no-brainer thing in D. So let's assume we require a program that will take a file name as a command line argument. But in some cases, this file should not take a command line argument, in which case it should use the contents of a default file which was available at compile time. Let me show you a function first how to do this both at runtime and compile time. It's a really boring in D because there's not much difference between compile time and runtime. Here's a function called parse, which takes the content as a single string, and it defines two lambdas inside for convenience. IsComment is given a line, if it starts with a hash character, it's a comment, and isSignificant means given a line, if that line is not empty, and if that line is not a comment, it's significant, I want to use it. And then I can use the following range expression, take the content, split it by new lines, pass all those lines through strip, which will strip the white spaces at the beginning and end of lines, and then apply this isSignificant filter on it, so the empty lines will disappear, make an array of them, which returns a string array. So doing this at compile time is done by using the import expression. At compile time, import take this special file name that I use at compile time, maybe default file.txt. That file is read, the content of the file is passed as a string to parse. Parses it, creates a string array, all at compile time, and then this default list variable is embedded in my binary, my program, that way, as the contents of that file. There are alternatives for making this compile time. You can use static const, which is the same thing as immutable in this case, or you can make it enum, which is not recommended for arrays, as in this case, or for associative arrays, because enum for arrays and associative arrays is generally more costly at runtime. So avoid that one, just be happy with immutable. And user code with this single function there and this default list object is remarkably simple. The main function receives arguments. If arguments length is 1, meaning there's only the program name, I will use default list. If there is more than one argument, then I will take arguments 1, call read text on it, which is a Phobos feature again, which reads a file and produces a string, and then I'll pass it to parse. The same code, simple differentiation between runtime and compile time lists. That concludes my presentation. I find D to be a very powerful engineering tool. I am very productive with it, and I still have very much fun with it. Thank you for listening.